This one in particular, it's at a beautiful venue. Pretty much everybody's staying in the hotel here. And so that means, after the sessions, people are going out and getting a beer and continuing the conversation. And it's just a great way to experience the conference.
Welcome to my talk about converting pure C++ shaders to pure C++ to compute shaders. So my name is Koen Samyn. Let's see. Oh, this is a good start. Doesn't seem to work. Just manually do the first slide. So I am the program coordinator of game development at DIE, which stands for Digital Arts and Entertainment. We have 6 majors in our study program, and some of the major are graphically oriented. And of course, our major is the best one. My colleague Tom is here as well, because we focus heavily on C++. I am not a C++ only developer. I also develop a tool called FXMath, which is an interactive mathematical tool. And in this tool, I also use compute shaders to show students how to create lighting effects. This is something for the graphical-oriented students that really don't like math. So maybe they hate me, maybe they hate math, but I need something interactive to show them what you can do with linear algebra and vector math. So why do I do this project? Our students focus heavily on C++, so they have to take on another language, in fact. So that mental load is quite heavy. They're still getting used to C++, still learning C++. And so it's sometimes hard to take on this extra concept. There's also a lot of ceremony for dealing with GPU resources, setting up a GPU context. Debugging GPU programs is pretty hard. Definitely for starting students. We are already happy when they debug their C++ applications. So definitely a difficult task. It's a different programming model. It's a different parallelism. You have work groups and threads. It's homogeneous parallelism, so every thread is doing the same task at approximately, well, they stay in lockstep with each other. And if they write C++ code, it can be hard to convert that C++ code into a compute shader, because they don't know what the requirements are of compute shaders. So they're dealing with a full port of existing code if they want to port it to compute shaders. Of course, this is not new. There's lots of existing frameworks. You have CUDA, you have Cycle. During some web searches, I also found CompuShady. Sounds a bit dodgy to me, but it's a Python framework. You have Slang, also yet another language to create shaders. And there's also, of course, OpenMP. So what am I trying to do? Something non-proprietary, fairly lightweight, and also an educational focus. I'm not trying to abstract away the entire OpenGL framework or compute shader framework. I'm trying to model it in a way that students can recognize the concepts. So I also see this as a step up to other shaders, so vertex, fragment, mesh shaders. So that's the next step in this project. Perhaps first, to create a mental model of compute shaders and why it's important for us in a game development study program to focus on that instead of more the other compute languages. We start from the CPU, which we call the host. and we run a C++ program. Seems appropriate in a C++ conference to use C++. And we talk to the GPU, which is also called the device. Naming is hard, so it's just a device. So the compute shader lives on the GPU. You have a program, but important for graphical applications, it can also talk to OpenGL resources. So the same IDs are used, ID in the sense of identifiers. So you have an identifier for a buffer. I can use it in a compute shader. I can also use it from an OpenGL window. So this makes it easy to communicate textures, buffers within those two different environments. Also important, it is really, you can really think of it like client-server programming. You don't actually, it's not a method call that you do when you execute a GPU program. You go to the driver and ask it to execute a program with a certain identifier, right? It's the same thing if you enter a form on the web. You're not inserting a record in the database. You're sending data to the server. Server interprets that and executes that and gives you the result back. So that's an important thing to keep in mind. So lots of problems come from the fact that this is actually a foreign device. You cannot just step through the code, although, well, you used to not be able to do that. Now there's a lot more tools that can do that for you. I had some experience with Qt. I don't know if anybody else knows Qt, but they had the slots keyword. And to me, that was like, okay, it works, but it's like polluting. I hope that nobody from Qt is here, but it's like polluting the language with your own keywords to make something possible. So that was a strong opinion that I had, to not introduce no keywords that do some strange stuff. Also wanted to work on compact code, and also, as I said, a close one-on-one mapping with GPU parallelism. And also I wanted to work on the same program, working on in the same way on CPU and GPU. Another design goal, perhaps not a design goal, but in university, we need to work on bigger projects sometimes. It's different if you work day to day in a programming job. We sometimes need the experience of making a larger project, and it's also an attempt to communicate with the C++ community to give us feedback on, yeah, this is not really the idiomatic way to do something, or this could be better. So this gives also something tangible for the C++ wider community to look at. So how does the process work? I'm trying to bring GLSL closer to C++. So I'm modeling some capabilities of GLSL. Maybe a bit shameful to say, but I wrote my own vector math library. That's perhaps the 1000th math library in. Yeah, I know. Correct. So also buffers, images, uniforms, image format conversion. So one big reason for compute shaders is the support for images, textures, and workgroups and threads. And also two backend systems. I chose OpenGL. It's a lot simpler than Vulkan. So because I don't, the compute shader infrastructure part was not the most important part to me. So the OpenGL code is a lot smaller than if I would have done it in Vulkan. Then I use Clang AST. I really like that library. I should qualify that. I like its capabilities, not necessarily its programming model, which is, it can be hard to look up information of that library. But what I do is I look at unsupported C++ syntax. On the GPU, you cannot create new. So you cannot use new and delete. You cannot work on the heap. And I generate an error or warning if a programmer would use an unsupported part of the syntax. Then, if the validation works, I do a transpilation step. I use the rewriter API for that. I export to GLSL. Again, there could be errors and warnings. I report them back in Visual Studio. And finally, a small pass, just to make absolutely sure that it works. I call the GLSL lang validator. I thought it was a typo, but there's only one L in that tool. And also generate an error or warning if something goes wrong there. So going to generate what's called in game development a couple of vertical slices of some cases that I want to support. First, a very simple one, just adding 2 vectors of floats. Then some ray tracing, always popular with the students. And then the game of life, which I have fond memories of as a compute shader. So let's start with what are we working towards to? What does a compute shader look like? First, the version is 430. That's version 4.3 of the OpenGL standard. You have a layout that defines a workgroup size. In simpler terms, if I have 100 things to do and my local size is 10, then I will have 10 workgroups of 10 tasks. So that determines the parallelism that we want to support. Secondly, we have the buffer concept. The buffer is not the data itself. It's just a higher level concept. It defines what you can plug into the execution of that shader. It has a name. The name is not too important. I haven't seen a real good use of that name, but you have to name it something. You have a binding, which is an identifier to make it easier to put stuff inside of that buffer. And it can be read-only. You can only read from the data. And finally, inside the buffer concept, you have your data itself. So you have a float array. We have a second one, second buffer, another binding number. So you have to typically have different IDs for your different numbers for your bindings. And again, a float array inside of it. Then we have something that we can write to. So another buffer with a float array inside of it. And finally, we have the main function. So this will cause some problems later. More, I would say, conceptual problems. When I also use the main, I'm going to prepare you beforehand. I'm also going to have a main function in my C++ code. Don't shoot me. Could be better. Could be Lambda as well. But I'm trying to keep it one-on-one with GLSL. I talked about tasks and work groups. You get the ID that you need to calculate from the global invocation ID. This is a 3-dimensional vector, and you get the X value out of that, and that gives you an index into your arrays. And then it's just a matter of calculating the result. Okay, pretty, well, more or less the simplest example, the hello world of compute shaders that I could find. So to reiterate, important, the buffer is not the data itself. It just defines like a slot, you could say, where you can plug your data into. And it encapsulates and defines what the data looks like. Also important, in the shader itself, I use A, B, and C, right? Not in A, or in B, or in C, so the arrays themselves. So what does my C++ equivalent look like? I have a struct. I use Clang annotate. Annotations are compiler dependent. You cannot just add annotations. Luckily, Clang has one where you can just call annotate and put in strings your own user-defined annotation. It's a float adder. So I have vec.hpp for the vector types. I have clang annotate. I'm going to use that to find my compute kernels in the AST. This is something that could be done better in C++26 with reflection to reflect the name of the struct. So for now, I have a file location where I can store the generated GLSL file. I have a local size that I'm going to convert. I have buffer bindings. So why am I doing it this way? So I have template parameters that allow me to more easily transpile that code into GLSL. So it's just in the code itself that it's a float and that its binding number is 0 or 1 or 2. So that makes it pretty easy to transpile this code. Inside my buffer binding, I then have a buffer resource, also of the same type. So in a buffer binding of float, you can only have a buffer resource also of float. So that's pretty neat. I have a main function inside my struct, and I have a namespace called TC, stands for tiny compute. I haven't trademarked that yet, so don't beat me to it. And also the same global invocation ID and the sum. Good. How am I going to validate that? I use Clang 22.0. There are matchers and visitors, and I wrote a custom tool that I call via CMake. This was like the most frustrating part of this project. As you can see, this is a dump of one of the kernels. It can get pretty complex, but the main thing is that you can get all the information of your source code out of this AST tree. So, for example, you can use a matcher to find all the structs or classes that are defined. So is definition. You can check, does it have the attribute annotate? Does it have a method with the name main? Does it have a field with the name file location? That is a const expression. And then you can also, that's very convenient, you can bind. If you find something like this, you can bind it and you can get that information back later. So if you have subparts that you need later on, this is pretty convenient. And then also it should have a local size field ready. Okay, then I can also, with the Clang AST library, I can also visit all the new expressions. So everywhere where there's a new, I can visit that. I can find out the line number and report to the user, you shouldn't do that. So, of course, only in compute kernels. Right. So here, for example, I use the format that Visual Studio uses for errors. I just output it in the error output, and then I can just click on it and see, okay, I did something wrong there. That's not supported yet. Good. Then the transpilation. When I transpile, I output the version 430. I skip includes. I also skip the struct. I also skip the file location. Lots of skipping. I rewrite the local size into the correct layout for a compute shader. I rewrite the buffer binding into correct buffer layout statement. So also for the other buffers. And then I output the main function. I strip namespaces, also not supported in GLSL, and I output the operation. So that's already a cycle of the process of converting C++ to GLSL. So now also I can execute that on two backends. So I have a GPU backend. I need to get the data from CPU into the GPU. So I have my backend has support for uploading buffers. Of course, you need to store that as unique pointers. I upload it. It receives a unique identifier. So you have A, B, and C. And that's done. Something that we tell our students, use RenderDoc for debugging stuff like this to see if it's actually on landed on the GPU. Then I activate the kernel. So we have now our data on the GPU. It's ready. I just need to connect this data to my binding slots. So I have bind buffer where I connect the data itself to my input slots of my compute shader program. And then I can execute that kernel, right? If it's on the GPU, I need to download it again to get the results back. All right, good. So typically only the C float array will be downloaded back as the A and B are not changed in this shader. So to change it to CPU execution, I just swap out the GPU backend and I use CPU backend, right? Something also for C++26, I know all the buffers that there are in the compute shader. So this is a bit of ceremony to execute it correctly, but this could be something that could be done via reflection. So I could just iterate over all the buffers and images and uniforms that are in the compute kernel and generate this code for me. Good. Okay. Of course, I have a bit of asymmetry in my application because, yeah, everything, if I execute it on the CPU, everything is already there. So my upload buffer doesn't make a lot of sense, but it's mainly for students to check if they actually did everything correctly to then be able to take the step to the GPU execution. So let's do another demo because I'm sure that nobody likes to see the result of a sum of two floats. So I chose to just show you the Raytracer demo to show you how it works. And how does it work? I just copy that image and I put it to the right. Bam, I have my GPU thing. So I can say what I want, of course, but let's look at the demo. I'm not as brave as Herb, so I recorded I recorded the source code. Yes, yes. Okay, so let's see. I have a let's go back a bit. So I have a sphere with a location, a radius, and a color. So I have 4 spheres that I want to render. I use that information to, that's a bit of math to calculate the intersection with the camera array. But now, let's see, I'm swapping, or I'm using my CPU backend. So I'm executing it, and I get my fantastic spheres. That's the beauty of recording it. I knew that was going to happen. And now I switch out the CPU backend and execute it again, and I should get the same result, right? Oh, shit. I recorded it, but still there's a disaster in the demo. Does anybody have an idea what went wrong here? Tom already knows. Anybody? It's, sorry?
It's random on CPU. The window is saying CPU Raytracer. Or it's like just...
Yeah, it's, yeah, I didn't change the title of the, but you can see on the frame rate that it's 130 FPS. It was mentioned in the keynote about if you use structs, right? There is padding that C++ uses, and GLSL does it differently, right? So my struct on CPU side does not correspond to my struct layout on the GPU side. So what is typically done is a bit hacking. I'm looking for a better solution for this. So I just combine the location and the radius into one vector 4. It's a bit dirty, but this is graphics programming for you. Something that I want to do is you can perfectly ask GLSlang validator or the GLSL tools to report back on the size of the structs on the compute shader size. You can compare that with the size of the struct on C++ and report an error if they do not match. Right? Checking if the layout matches. So I changed that. I also have to change it when I ask for that information. So this is also something I cut it out of the presentation. But if you want more information about it, you can come and ask. So I have a user-defined literal. So on GPU side, swizzling is a big thing. So if you have a vector 4, you can ask for, give me .xx,yz. So it just gives you the first component of that vector and then yz. So it's a bit of combinatorics. You can take 4 out of 4 with repetition. So that's a lot. I forgot how much it was. I think it's in the 300 combinations that you have. So you need some kind of system to do that efficiently. Okay, so that's done. I also need to adapt my spheres that I create here. So it should be vec4s now, and the radius should be part of that vec4 definition. Okay, I'm still doing good on time, I hope. So this would be painful to type while everybody's watching. And then when I start it, it's in fact fixed. So it's the same code running the same Raytracer, right? So, okay, cool. Happy that the demo went well. So game of life. It's a very good exercise to make if you want to get serious about compute shader programming. So why is it so good? You can think about, this is a small grid, but you can think about what do you need to do if you want to make it arbitrarily large on the GPU. For example, performance things that you can do is checking if a certain region does not have any cells, so you don't need to run the algorithm there. One small thing is it's a convolution. So if you have the border cells, you need to be careful not to sample them. So one possible solution is to add a halo around the world, and then it doesn't matter if you go over all the neighbors of the cell. So for those that don't know, it has only a couple of rules. So if a cell is empty or dead and it doesn't have any live neighbors, it stays dead. If it's alive and it has 2 or 3 neighbors, it stays alive. And if it's dead and it has 3 neighbors, then it becomes alive. So simple rules create a lot of interaction. And that's also part of why it's good. It's an animation, so it's a state that evolves. So for our students, that's also perfect because they like to see things move. So one example, I rendered this with One Lone Coder game engine, also pretty good. So it's, this Pantomino generates, I think, about 1,000. It stays alive for 1,000 generations. I didn't show them all, but that's a nice use case to do. So let's see. We have to support images. There's one important function that I need to support. that's image load. And it's pretty complex. So on this slide is one part of the complexity of it. Next slide, a bit more complexity. So you have all these different types of images. 1D is, for example, a gradient. Cube is, for example, a skybox texture. So you have 3D images, 2D images, image arrays. So yeah, you have lots of combinations. You have a prefix for the image. So in this case, I have I image, which means that it returns an IVEC4. That's one saving grace. It always returns something with 4 components. So it can be a different type, but the number of components is always 4. And some of those are linked, of course. There are 27 combinations. For example, if it's an unsigned image, then it returns a UVEC4. Okay? You don't want to write all those 27 combinations, obviously. You want some kind of code, preferably one function that does all of this. So there's also more. It's not only about the image types or the representation types. It could be that you have a source image that's a grayscale. It only has a red channel. And the destination, you want to load it in, you want to use it, but you want to use it as a float. Why? Because you want to do lighting calculations. And the lighting calculations, you need floating point operations. Okay? So you need to convert that data into a float. So from 0 to 255, you need to divide by 255. Also, we always want 4 components. So we have, we need to pad that information there, right? We choose 0 for color channels, and for a transparency channel, it's 255. Otherwise, everything would be transparent by default. And if we read from that image, we're going to get 001. So that's one part of the complexity. So on top of these combinations, we also have the types of the images and the types that we want to use. So we call that the external format, meaning it comes from outside, could be loaded from file, doesn't matter. And we have the internal format. People that have already programmed, I'm scanning the room to see if I see a frown. Okay, I'm safe. That's not the entire story, but for now, good enough. Okay, and then you can define that. So you have the internal format. You say it's an unsigned image. It's a 2D image. So you can load from it. So it's unsigned. So you get back an unsigned VEC4. You do some convolution, and you store it back in the image. Right? So you have to, it's symmetrical in this case. You get the UVEC4 back. You need to store a UVEC4 into that image. Good. So all the complexity. We have the dimension, right? It's one-dimensional, two-dimensional, three-dimensional. We have the external format. So it could be also the number of channels. Could be an RGB image, could be an RG image even, an RGBA. We have to convert that data or even pad that data, and then we get our internal format. Right? So the whole chain is pretty complex. So the big question for me was, can I do this with one function? And also, additionally, this is the hot part, right? Image load is going to be called at least for all the pixels that you want to generate, and image store as well. So yeah, we don't want runtime branching in this code to differentiate between different scenarios. So it has to go via templates, traits, and const expressions. So I really want to that was the goal, at least, to make it so that you don't have any branching on like the external. If external format is RGB, then do this, else do that. So that would be pretty bad in this function. So we're going to first look at the buffer resource to update it, to make it into a multi-dimensional buffer, possibly. So we're adding a template parameter with the dimension. I think also this is something with the multi-dimensional spans that are coming that I will probably swap out once I get to C++26, but I started out with C++20. I'm using a one-dimensional data backing, fairly typical. And I initialize my buffer resource with the appropriate dim type. So not with the full size, but I want to be able to say, I want to create a buffer resource with width 640 and height 480 to make it more readable. So the dim type, what should that be? It should be int32t for one-dimensional data, IVEC2 for two-dimensional, and IVEC3 for three-dimensional. And there's a simple reason for that. And I'm not using size t, but also to correspond with GLSL, I'm using int32t as base type for indexing. So I can initialize it, but still have a problem. I need to initialize my backing data with the full size. And also, I want to have an index operator, also with the correct dim type. So I want to sample from an image. I want to say, give me pixel at 100, 300, for example. So also as a two-dimensional vector. And also, if I have a two-dimensional coordinate, I need to be able to convert it back to a one-dimensional index. All right. So how do we do that? With traits. This is something that I think is a good thing to step into as a student. It's fairly readable. It gives a good idea what you can do with templates. So I have my enum class dim for all my 3 dimensions. I make a traits template, and then I specialize it on the dimension. So my index type is int32t. This is something that I find is a major advantage of C++. This index type does not have to have any relation with the other specializations that I'm going to make. In other languages, there needs to be some kind of inheritance relation. But with C++, it's like, okay, you just define it and it works. Yeah, for one dimension, I don't do anything. It's just the index type is an int32t, so I just return that as is. For 2 dimensions, it's an IVEC-T as index type. Flatten, I didn't explain that. So flatten is basically you hit a 2-dimensional coordinate and you hit it so hard that it becomes 1-dimensional. So you just use the size. So you have to know the width and height of your 2-dimensional buffer, and you convert that into a index, 1-dimensional index. And then also, if I have, again, an image of 640 by 480, the total size of my vector will be the product of those 2 dimensions. And same thing for 3D. I haven't used 3D buffers yet, but it's possible to extend this into tensors and what have you not. Okay, so the buffer then becomes templated on the dimension. So I can just create buffers that are 2-dimensional or 3-dimensional in nature, but of course always with a 1-dimensional backing. So I use those traits to define my dim type, to define the product, so the total size of my vector, and also to convert multi-dimensional coordinates back into a 1-dimensional index. All right. As said, I found this pretty interesting. This is an example that I would use for students if I don't get negative feedback on doing it in this kind of way. But something like this is I think, also a bit different than the classical exercise of write your own container type in a templated way. So it's a bit more interesting, I think. All right. Then, so we have the dimension covered. We need to look at channels. So we have all the different possibilities. So you can even have different ordering of your channels. So I'm using the STB image library. I thought STB was some kind of fancy abbreviation, but it's the initials of his name. And I forgot, yeah, old age. I'm above 50, so I forgot his name. Shame on me. Anyway, if you load it with STB image, it can be in any format and those orderings of channels. I suppose there are other image loaders that even have funkier formats, but I'm not covering these. It can be that you're doing simulation type stuff, that you have floating points that you are doing something with. So it can be literally that value that you want, right? You're doing a weather simulation or whatever. So it can be that literal. It can also be that it's a float between -1 and 1. It can be an unsigned float between 0 and 1. You have the integer type, so lots of complexity there. You also have the representation. So 8-bit types are pretty common. 16-bit types are also common. Float 16 is something that I will need to go to C++23 for. There are some libraries that do it within C++, but I would like to stick with the standard. And then you also have the packing. There are some funky formats in there. The most usual ones are same number of bits for each channel, but you have some formats where red channel is 5 bits, green channel is 6 bits, and blue channel is 5 bits. So you have 16 bits. That's like a 2-byte color. There's even one very special format that's 3 floats, and they share a 5-bit exponent, and they have a 7-bit mantissa, giving you 32 bits. So it's the external format world is really interesting, weird, and frightening. Okay, so I cannot just say that I have an easy way to get R, G, B, and A from something, right? I could model it in a kind of straightforward manner, but I wanted something more flexible to be able to support also the weird formats in the future. So, small example. For example, suppose I have an RGB8 pixel. So RGB is present and it's a floating point. I can, so that's with the design. I would get the channel information in a templated way. So not directly by just saying px.r, but I'm asking the pixel, give me the information of the red channel. If I ask for information about the alpha channel, then this becomes a padded value. So this system gives me a way to create virtual channels, which is important, of course, because pixels are part of an image, and you cannot just like add information into the image itself. You want to keep it like it is. Yeah, that's part of a testing framework to see if my code works. I'm using Google Test, which was very useful in this project. This is very simple, of course. All the channels have the same type. Might not be the case for a couple of formats. All right. So what do I also want to have is that I can ask what the type is of the channel. So I'm also want to do this in a templated way. So I have the RGB8 type. I want to be able to ask that type what type do you have for your red channel, what type do you have for your green channel, and all the other channels, right? So yeah, it's fairly possible. I looked at the number of bits that could be used to model an integer, and you have everything from 2, 4, 5, 6, 10, even 11 bit types. So that's all possible. So I have a pixel concept. I'm starting out with a channel concept. Also something that I think we need to be able to give to our students. So what does it require? That you get a type. The get function should be convertible to that channel type. And the set function is a bit easier. It just has to accept what the get function gives back. And then you can make a simple pixel concept. If you have a pixel, it should support returning back channel information, right? So the pixel itself could be simple for the most simple types, but could also be something more complex. All right, then we have the conversions. So unsigned byte to float. And how did I do that? Also with templates, of course. So I have a channel converter, which converts from a source type to destination type. If the two types are the same, it's a no operation. And from uint8 to float, it's division by 255. Okay, I went a bit fast. Okay, and in this way, you can create all the converters that you need and expand the fidelity of my image support. All right, so let's see. I have to keep track of time. We also want an image binding. Similarly to the buffer binding, you specify what the internal type is. So, for example, only a red channel, 8 bytes, 8 bits, unsigned int, a dimension, a binding number, and then ultimately the external format type. So they can be the same, but that's, yeah, you can mix and match as you want. And of course, the buffer resource has to correspond to the external format and have the same dimension as the image binding itself. All right. So we have, for example, our internal format. So again, we can. It could be possible that you have to pad the external format. It's also possible that you have to pad the internal format. So it's like you have to add channel information on both sides sometimes. One thing is that's not the full story. If you upload an image to the GPU, it also stores it internally, right? Which makes sense if you have a image with 32 bits for each color, and you upload it, and the driver converts it into an image with 4 floats. You have an explosion of your image size, which is not very helpful. If you listen to the keynote talk this morning, even though it stores it in this way and you will need an extra conversion, it's still worth it because you have only 1/16 of the data that you need if you would store it with 4 floats, for example. So the conversion is yeah, practically it's a blip on the performance. And also, yeah, it's a vec4 that I return. Good. So we pad on the incoming side. We can also pad on the internal format. So I can say, I need the information from the red channel. I'm going to use the minimum of that channel format for the green channel, the minimum for the blue channel, and the maximum for the alpha channel again. So padding is needed both on the incoming image and the outgoing image sometimes. Then finally, okay, I got there. There's the image load. which is purely templated. So all possible combinations, all conversions are just one function. So I have the internal format, the dimension, the pixel concept for the external format. I'm still thinking maybe it should be first the external format and then the internal format, okay? But anyway, I have a templated function. So the texture coordinate also adapts to the dimension. I get the buffer data. I removed static asserts to check if buff is not a null pointer, just for making the number of lines a bit smaller. I query the buffer for the pixel data, so it should be the same as the pixel concept. Yeah, my colleague Tom said, why do you do this? It's a bit extra typing. For me, I'm still getting used to concept, so I have a destination type, which comes from my GPU format traits. I have a vector type that I should return. And then I can just load the information from the pixel. Right? The pixel itself knows what type it is. It knows what type it should convert to. And finally, I can return that vector type. Okay? I also feel for me, this was like a confirmation that this is a pretty powerful system, because in GLSL, you always have to return a vector 4. And here I could even say, that's not necessary. I only have one channel, so I just return a float, for example. So I know as software programmers, you sometimes get into a situation that you feel like, I really have to like stress and work at it to get to a solution. And here I feel like I still have margin to do extra stuff. So which is nice to see. Let's see, I have 8 minutes. So how do you use it? You use an image binding. So internal format, external format, dimension is 2. I have 2 bindings with 0 and 1. I also wanted to show you this. I have a standard array of size 8, which defines the neighbors I want to sample. It's going to be pretty neat in a moment, I promise. So you have uvec2, which is the coordinate that you have to do work on. I'm adding the padding. Remember that border that I put around the world. And I'm going to count the neighbors. Also, something that was nice to see in Clang, this is an implicit conversion, right? It's converting from a byte to a bool. In C++, no problem. In GLSL, problem. So I'm going over my standard array. I count the neighbors, so it's 0, 1, that information. I calculate a new state, and I store it into my output image. If I then transpile, I lose the struct. I create the layout bindings. Uniform, haven't talked about that much. You can see that as a parameter for the compute shader. I convert the standard array into a GLSL array, which looks a bit weird because you have kind of a repetition of the size of that array. Strip the namespaces. This stays the same, only the formatting is a bit nicer because Notepad formats GLSL quite nicely. The number of neighbors. Here we have that I can detect with Clang AST. There was an implicit conversion there, and I can then rewrite that to an explicit conversion. Next one is kernel indices.size, which is of course not supported. Yeah, it should be k indices.size. Not supported, so I replace it in my rewriter with the actual size of that standard array. Yeah, this one is also the same. We have a Boolean new state. Yeah, and also I can create, so that's something that's allowed. I can use new state to create my uvec4. All right, and then yeah, my game of life works on CPU and GPU. On GPU, it works at about 166 frames per second. On CPU, in debug mode, it's 2 or 3 frames per second. But you have something that you can debug if something goes wrong. You can see, okay, what was, fix the error. Maybe work on a smaller world size first. And if it works on CPU, you can upscale that. All right. So I have 3 vertical slices. There's still much work to do in this project. So I have to go horizontal, support more image formats, more GLSL functions. I can draw the conclusion that generic programming reduces code. So it's really small code, and you can read it, and you can add stuff to it via traits. So it's really powerful to use these things. And I think, so part of this program was to be more familiar with generic programming. And it's really, the code remains flexible, but you don't have any performance hit. And I also need to upgrade to C++26 because it's like, to bind those buffers and these images, that's really code that you do not want to write because it's like pretty deterministic what you need to do. Okay. Also don't want to like have a vector of image bindings and then iterate over that vector. That's like polluting the code with stuff that's not necessary. And reflection. All right, any questions?
Can you
can go to the microphone?
can you chain these compute shaders?
Yes. So I have an example for my Raytracer, for example. I generate a camera rays with a compute shader. So it outputs an RGBA image, a floating point image with the ray information. And then I can bind that. So I can just attach that buffer to 2 bindings, right? So 2 buffer bindings can point to the same buffer. So in that way, I can use the output of one compute shader as input for the other compute shader. So it's really kind of a, sometimes look at it in a functional way. You have like a flow of information, a data-oriented way of organizing things.
Okay. Thanks.
Yep.
And another question, have you considered like going to SPIRV type of format instead of GLSL?
Yes, but in the end, I didn't have the time. I didn't have any experience with that.
Okay.
I had experience with rewriting source code, but didn't have any experience with like, then I would go to LLVM, I guess, to like generate intermediate code, and then that intermediate code could be processed by SPIRV.
Yeah.
But it was a risk. I mean, I also have lessons to prepare and other stuff to do. So yeah, the time was a bit, but I really think that's the direction I would go. But it would be more like something that I would give to my students to make them struggle.
Yeah. Thank you. Thank you. Great talk.
Yeah.
Thanks for the interesting insight on the other side of GPU programming. In your adder kernel on, I think it was slide 34 or something, you also have to copy in the C data.
Yes.
Even though it's only a result.
Yeah.
So is this really a copy operation to the device?
Yeah, that's a very sharp insight. Very good question. It is indeed sometimes with the current system. For example, I render the texture for the ray tracing. I don't need to have that on the CPU. But right now I need to make like a dummy image with the correct size and empty data to upload it to the GPU. But I'm looking there for a better way to probably have something like a, I don't know how you call it, a proxy buffer or something, which just has a size and no vector backing it, just to be able to initialize it on the GPU. But yeah, that's a good remark.
Okay, thank you.
Thank you so much for the talk. One small thing. I was wondering, in the example where the demonstration doesn't work, does Pragma Pack just fix this?
Yes, but yes and no. I want to do it in a portable way, right? So, so we need, as teachers, we need to be careful to like give students like tricks and tips that might not work on other platforms. Definitely in game development, where the code could be, on consoles or Mac or whatever. So I'm looking like for a robust solution. Perhaps the best solution is just to give an error, like, okay, it doesn't match, make it match. And that's also one thing. For students, you don't want to like clear out the path, clear out every problem. It's sometimes also necessary to see, hey, this is like a typical problem that you're going to have. So sometimes we have to make them stumble and hit their head and make them bleed to to let the lesson land. Sorry, I'm channeling my inner Tom here. All right.
Thank you so much.
Okay. All right. Thank you. And